This is lecture 15 for Physics 220. We're going to continue our theme of calculating a force on charged particles as they move in the presence of a magnetic field. Only this time we'll think about the charged particles in wires, and they have a force on them, and since the charged particle as they're moving in the wire creating a current have to stay in the wire, this effectively makes a force on wires. So let's see how that works out. Oh, looks like I have, first of all, a top 10 list. These are 10 more bad analogies from high school writing. So, number 10, he spoke with the kind of wisdom that can only come from experience, like a guy who goes blind because he looked at a solar eclipse without one of those boxes with a pinhole in it, and now goes around the country speaking at high schools about the dangers of looking at a solar eclipse without one of those boxes. Number 9, she grew on him like she was a colony of E. coli and he was room temperature Canadian beef. Number 8, her vocabulary was as bad as like whatever. Number 7, the revelation that his marriage of 30 years had disintegrated because of his wife's infidelity came as a rude shock, like a surcharge at a formerly surcharge-free ATM machine. Number 6, long separated by cruel fate, the star-crossed lovers raced across the grassy field toward each other, like two freight trains, one having left Cleveland at 6:36 p.m. traveling west at 55 miles per hour, the other from Topeka at 4:19 p.m. traveling east at a speed of 35 miles per hour. Number 5, he fell for her like his heart was a mob informant and she was the East River. Number 4, even in his last years, Granddad had a mind like a steel trap, only one that had been left out so long it had rusted shut. Number 3, the young fighter had a hungry look, the kind like you get from not eating for a while. Number 2, he was as lame as a duck. Not the metaphorical lame duck either, but a real duck that was actually lame, maybe from stepping on a landmine or something. And the number 1 bad analogy from high school writing is, he was deeply in love. When she spoke, he thought he heard bells, as if she were a garbage truck backing up. All right, onward to some physics work. So, we have a wire. We know that if there's a current in this wire, maybe the current is going up this way, current I, that we really have some charged particles in there moving, causing that current. And those are going to have a force on them. In fact, this wire doesn't even have to be straight. It could be bendy around through some field, which might also vary with position. Okay, so let's think about what kind of force would be on some little piece of wire that has some length. So first of all, the force is going to be Q times the drift velocity of a charged particle, how fast it's going down the wire, cross B. That would be the force on one particle in there. But we know there's many charged particles altogether making a current. So let's multiply by the number of particles. And I'm going to do it this way. N will be number of particles per volume. And then I'm going to multiply by the volume of a little chunk of wire. So cross-section of the wire times the length of the wire. So cross-section, cross-sectional area. So cross-section area. And then we have length of the wire segment. Okay, so then this will be the total force on the wire segment. So just to rehash this, we've got the force on one charged particle, and then we multiplied by the number of particles, which is the number per volume times a volume in some chunk of wire. And there we have it. That will be our force. So we can write it this way. Force on this piece of wire will be current times, I'll put a vector on this length of wire so that runs along the direction that the current is flowing. So orient that length vector, so as units of length, but just a vector pointing along the direction of the wire, cross B. Now, we learned this before, that the current in the wire equals the number of particles per volume times the speed that the particles are drifting times the cross-sectional area times the charge on a particle that's producing that current. So we just started with our original formula that tells us the force due to a magnetic field on a moving charge, and we quickly got to, hey, this will cause a force on a segment of wire that has moving charges in it. All right, so let's do an example. Let's suppose that we have a chunk of, or this funny protractor-shaped wire, so a straight segment with an arced segment, and we have current going around here. So the current is flowing like this, going around this wire, and we'd like to know what is the force on this wire that has this current in it. All right, so let's do the easy part. Let's do the force on the bottom segment. So we have the current is flowing to the right, and we have, so that our vector L will be to the right across B. All right, and our B field is shown to be pointed upward in the plane of the page this way. Okay, so these are perpendicular, the wire and the magnetic field. Okay, so let's put in our values. We've got the current, and then how long is our wire? Well, notice that we have a radius of this arc, so the straight part across the bottom would be 2 times that radius. Okay, so here's our length, 2 times the radius, and it is pointed in the x direction. All right, and now we have to cross that with our B field, which happens to be pointed in the y direction. So we'll put a j hat there. So I cross j hat, those are perpendicular, and you can actually use your right hand to help you do cross products. So you can cross your fingers from I toward j, and if you can think that through, you'll realize that's going to point in the k direction. So the answer ends up going in the k direction. I cross j equals k. And then all those other things that are there, we have 2 times the current times the radius times the magnetic field. There's our force on that bottom segment of wire. If you like, let's just do this little aside. I cross j. How would that look if you did it as a determinant? Put the ij k across on the top, and then your first vector is in the direction of I, so it's everything there, and 0 in j and k. Your second vector is everything in the j direction, so you're trying to do this thing, and this will only have an answer in the k direction. It'll look like k direction times 1 subtract 0 when you do those two things that subtract, and that equals k. Okay, but you can just straight away say that I cross j is k if you can think that through in your mind. All right, let's do the loop segment. So the force on the loop segment of our wire, that's going to be our current. But now we need to be a little careful because our direction keeps changing. So here's the direction there, the directions, all these different directions that L is pointing, and so what we're going to have to do is integrate dl. Now cross products care about their order, so dl cross B is different than B cross dl. You could flip it, but that will cost you a minus sign. All right, so we're going to add up all these little segments crossed with the B field in all these different ways. So here's how we would do that. We'd put I times, and I think what I'll do is write this integral in terms of an angle. So a small angle times a radius gives me a little piece of that arc. So I can integrate 0 to pi of a radius times d theta. Okay, but I need a vector. I have to have a vector that points like these little blue arrows, and everywhere it's different. And so if I think about this, my unit vector, I could write it this way, minus I, sine times I. If you have a sine and a cosine, when you square those and add them together, you're guaranteed to get 1. So this is a unit vector. But let's just think this through, if this looks right. So I'm going to make a little note. This is a unit vector tangent to the loop. And not only is it tangent, but it's pointing along the direction of the current everywhere on that loop. So let's see if that makes sense. So when theta is 0, we're over here at a point right here, the beginning of our integration, and we should have a unit vector that's pointing straight up. So when theta is 0, sine is 0, cosine is 1, and we get a vector pointing in the j direction. On the other hand, when theta is 90 degrees, or pi halves, up there at the top, then you'd have a unit vector. The cosine would give you 0. The unit vector would point in the minus I direction. That sounds good. And then finally over here, if you put in 180 degrees or pi, you'd get cosine of pi is -1. You'd have a unit vector pointing downward in the j direction. There'd be 0 in the I hat direction. So that appears to work. That gives us a unit vector pointed along dl. So we have all these little tiny arcs, length r times d theta times a unit vector that's the right way. Now we need to put our B field in there. So this is crossed with our B field, which happened to be strength B in the j direction. All right, now you could set this up as a determinant to get your cross product done, or you could also say, if I have I cross j, I'm going to get something. When I do j cross j, those are parallel, and that gives me nothing. So I only have one piece that survives. I cross j, as we just talked about, gives you a k direction. All right, so this is going to end up, I'll pull some constants out of this integral. I have I r b integral 0 to pi d theta, and looks like the only surviving piece is that first piece, the I cross j. So I have the minus sine theta, and the direction now has become k hat. All right, so now I need to perform that integral. That's not too bad. That's going to give me IRB, and I have the answer to integrate minus sine becomes positive cosine theta, 0 to pi. All right, and this is in the k hat direction. Of course, when you evaluate those, this gives you -1, subtract 1. So the answer ends up being minus 2I BR K hat. All right, oh, look at that. It's equal and opposite our previous answer. So the bottom segment of wire had a force that was upward, and the curved segment of wire, in spite of it being a longer segment of wire, in this uniform magnetic field, it ended up giving me a net force down opposite that was equal. And so the force total, which would be force on the bottom plus the force on the loop, that would actually be 0. All right, so that's a pretty involved example. We basically did 2 problems in one there. All right, let's do some quiz questions. We have a wire passes through a region with a magnetic field. Which figure best depicts what will happen when the current in the wire flows upward? So we have upward flowing current. We have 3 pictures here. One, the wire is deflected, not deflected, or deflected to the left or to the right. What do you think? In the magnetic field, of course, you can see these arrow tails here is pointed into the page. Okay, so the answer I get is B. It's pointed, the force is to the left, and I can use my right hand to point my fingers in the direction of the current and then curl them into the direction of the field and end up with a current that points, or a force that points leftward. All right, actually this is the same problem, I believe. So the current passes through a segment of wire in a uniform magnetic field. The force on the wire segment is due to the magnetic field. The magnetic field is directed up, down, right, out of the page, or none of the above. And the answer is none of the above because it's left. Here's the force. Using the right-hand rule, you'll come up with it's deflected leftward. Current flows counterclockwise around a loop of wire. The net force on the loop due to the magnetic field is directed up, directed down, right into the page or out of the page. And the answer is the net force is 0. Right? So when I look at this, I find that every little section of wire, there's a little DL that goes around this way. It's such that it's giving a force on each section of wire inward. And this is happening all the way around the wire. And it's symmetric, so all these forces should balance and give 0 net force. All right, so that brings up a new topic. What happens when you have a loop of wire? You can sometimes get a torque, even though in a uniform magnetic field there will be no net force on a loop of wire. There can be a torque on it that makes it want to spin as opposed to move altogether. So here we have this magnetic field coming through here from the left to the right, uniform, and we have this current that's going around this loop like this. And so let's see what's going on here. Well, we have 4 sections of wire. Notice that the top and the bottom, I'll call it force on segment 1 and force on segment 3, they're just 0. And the reason is the current is parallel to the magnetic field, and the cross product between parallel vectors or anti-parallel vectors is 0. So we just need to worry about side 2 and side 4. All right, so let's look at those forces. The force on side 2, it's nice and perpendicular. Its magnitude will be current times the length of that. This has, I guess we'll call this one, here it's shown, length A. That's how tall it is, length A. And down here we have length B. Okay, well, on side 2, we have the length, which is A, times the B field. And this is going to be with a cross product. When you do this carefully, you find that this gives you a force, which would be into the page. So that's the direction. Oops, I lied. That's out of the page. Need to do my right hand rule a little more carefully and think that through. So that one's out of page when you check that carefully. Now, on the other side, we have I equals A times B, and this one's into page. So I can take my right hand, point my fingers in the direction of the current, and curl them. So I have to do that, curl them into the B field, and then I end up with the thumb pointing into the page. So be careful when you're trying to line up your right hand with the drawing on your paper. Sometimes you might get in some funny positions and get carpal tunnel syndrome or something. All right, well, we're ready to figure out a torque. So what would our maximum torque be? This will be because we've lined up perfectly to get the most torque possible. What I would do is take a lever arm. So let's take the rotation axis to be right down the center. So you have a force that's out of the page on the left and into the page on the right. That's going to make it want to spin about that axis that I just drew. And the radius out to where the forces are applied are half of B, from the center half to one side and half to the other. So here's our lever arm. To get our torque, it'll be a lever arm B halves times the force on the left, which is out of the page, and then the force on the right is into the page. Those are both helping make the torque. And so I can substitute our formulas in there. We'll end up with AB times IB. Each one contributes equally to it, and that doubles it up and gets rid of that too. So there is our torque. In fact, I'm going to write this as AIB, where this is the loop area. A times B is the loop area. In fact, we used a rectangle, but it didn't have to have a rectangular shape. It could have a weird circle shape or oval shape or strange distorted shape. If you make a loop of wire that's like this in a plane, you're guaranteed that the torque, the maximum torque, depending on how it's rotated in the field, will be the area times the current around the loop times B. It doesn't have to be a square shape. All right, now if you allow that to turn a ways, the torque will change. So the torque in general will be AIB, and then times a sine of an angle. And this will be the angle between the B field and a perpendicular to a vector or unit vector, if you will, perpendicular to the plane of the loop. Okay. If I can write loop a little better. Okay. Now, one last thing to do is to mention that this area times current has a name. I can erase that. So this name is called, well, we use the letter mu. It's a Greek letter mu. It looks like an M. And we call that magnetic moment. All right. So that's what we have for torque on a wire in a loop. And in fact, you can make a motor this way. So if you have some loop with current that you force through this loop in the presence of a magnetic field, it's going to put a torque on it, and it can cause this loop to pivot. On the other hand, once it pivots, it won't want to keep pivoting, and so what you do is reverse your current. So every time it rotates about half a turn, you change the direction of the current, so you keep it wanting to keep rotating around and around the same way. So that's how to make a motor. All right, so let's do some quiz questions. Which situation has the largest torque on the loop? So we have a side view here showing a current going around in the presence of a magnetic field, and then we have top views. So we have two top views. So top view A and top view B, and we're our magnetic field here. I usually make them green, but these look red. These are magnetic field lines here. Okay. And the question is, of these two situations, which one would have the most torque? And the answer is A, because the cross product will work the best. And let me say what I mean by that. There's a sine of the angle here. You'll get a bigger sine of theta, because here your magnetic moment, or that area vector, is pointing that way, perpendicular to your area, and it's in a direction that is most perpendicular. That is, most perpendicular to the field. So our magnetic field, that's what matters. So here's our magnetic field going this way, and they're perpendicular. So that's the angle. Sine of 90 degrees is going to give you the most torque. In the other case, the forces, the magnetic field is pointing this way, and you have the area vector that way. That's less than 9 degrees, or it might be more than 9 degrees, but in any case, it gives you a sine that's not as strong as when you have 90 degrees. And so there's less torque in B. So current flows counterclockwise in a loop of wire. The torque vector for the loop is directed up, directed down, directed to the right, or directed out of the page. Okay, so the torque is actually, you can write it this way as a vector, and that would be the magnetic moment cross with the B field. That's where that sign comes from. So we're used to tau equaling mu B sine of theta. All right, so we have the vector for this area loop is out of the page. And we actually have a convention. If you use your right hand and have your fingers point around the loop in the direction of the current, then your thumb tells you the convention we have of which direction of the two possibilities to make the perpendicular vector. So the magnetic moment's out of the page. But the point is the magnetic moment and the magnetic field, which is into the page, those are anti-aligned by 180 degrees, and the sign of that vector is 0. So actually this one has 0 torque on it, the way it's oriented. All right, the units of magnetic moment are, so we're looking for units on mu, and the magnetic moment, as we remembered, is area times current. And so A is your answer to that, current times area. All right, we'll see you in the homework help video.